Okay, we've all seen it, right? That brilliant flash that just rips across the sky, and then, boom, the thunder. But have you ever stopped to think about what lightning actually is? I mean, it's so familiar, but it's also one of the most misunderstood things in nature. So let's really get into the physics of it, because trust me, the reality is way more extreme than you can even imagine.
And when I say extreme, I am not kidding. We're talking hotter than the sun, faster than a bullet doesn't even come close. Its return stroke is a third of the speed of light. And get this, it literally creates antimatter. Yeah, you heard that right. So stick with me because we're about to figure out how any of that is even possible.
All right, first things first, before you get that massive spark, you need a power source, right? And in this case, the storm cloud itself transforms into this colossal battery just hanging out in the sky. So the big question is, how does it even get charged up? Well, it's actually a pretty straightforward process, just four basic steps. It all starts with these powerful updrafts that suck moist air way up high into the freezing parts of the atmosphere. Up there, you get a mix of tiny light ice crystals and these heavier, slushy hail pellets called graupel. Now, inside the cloud, it's total chaos. Everything's bumping into each other. And when they collide, they're literally stripping electrons off one another. The light little ice crystals end up with a positive charge and get carried up to the top, while the heavier, now negative graupel sinks towards the middle. And just like that, the cloud is charging up. So what you end up with is this really cool electrical structure. You've got this huge positive layer at the very top of the cloud, a massive negative layer right in the middle, and then even a little pocket of positive charge at the bottom. But here's the kicker. That huge negative charge in the middle pushes away all the negative charges on the ground beneath it. So the Earth itself gets this strong induced positive charge, just waiting, practically begging to connect with the cloud above. The whole system is primed and ready to go. Okay, but this is where the story gets really weird. For decades, scientists figured, hey, let's just measure the electric field inside these clouds. So they sent up balloons, they flew planes right through them, and the numbers they got back just didn't make any sense. It created a huge paradox that left physicists scratching their heads. They called it the breakdown paradox. See, air is actually a really good insulator. It doesn't like to conduct electricity. To get a spark to jump through it, you need a crazy strong electric field to, break down that insulation. But the fields they were measuring inside these powerful thunderclouds, they were about an order of magnitude. That's 10 times too weak to do it on their own. It just shouldn't have been possible. I mean, just look at the scale of this problem. We're measuring fields of, say, 100,000 volts per meter. But basic physics tells us you need something closer to 1,000,000 volts per meter, maybe even more to get a spark going. So you have this fully charged cloud, you have the ground just waiting below, but there just isn't enough juice to make the jump. Something big was missing from the equation. So how in the world is lightning even possible? If the cloud can't do it by itself, what's pulling the trigger on this incredible discharge? Well, the answer, scientists now believe, is that it needs a little help, an outside trigger. There are a couple of big theories. The first one is pretty wild. It suggests that high-energy cosmic rays, particles from deep space, are constantly bombarding our atmosphere. When one hits just right, it creates a little shower of charged particles that basically carves out a temporary, easy path for the electricity. The other idea is a kind of internal chain reaction, where the cloud's own field gets a few electrons going so fast they start shooting out X-rays, and those X-rays knock loose even more fast electrons in a runaway avalanche. Either way, it seems the cloud needs a key to unlock the path and open the floodgates. Okay, so with that mystery solved, we can finally get to the main event, the flash itself. And you might be surprised to learn that the lightning bolt you see isn't just one single thing. Nope, it's an insanely fast multi-step process. Here's how it goes down. First, there's a little breakdown inside the cloud. From there, a channel of negative charge called a stepped leader starts snaking its way down toward the ground in these jerky 50-meter steps, kind of feeling its way out. As it gets close, that positive charge on the ground gets excited and sends up its own little sparks, called upward streamers, reaching for it. When one of those streamers finally connects with the leader, bam, the circuit is complete. And that's when the real show begins, the return stroke. The moment they connect, an absolutely unimaginable surge of energy rockets up that channel from the ground to the cloud, heating the air inside to around 30,000 Kelvin. Now, to put that number in perspective for you, that is 5 times hotter than the surface of the sun. And all of this is happening in a channel that's no wider than your thumb. Just incredible. And the current? The sheer amount of electricity flowing through that tiny channel peaks at a staggering 30,000 amps on average. And here's the crazy part. The whole return stroke, that bright flash that we actually see as lightning, travels from the ground back up to the cloud at about one-third the speed of light. It is an event of just truly cosmic violence. But as incredible as all that sounds, we've just been talking about your average, everyday lightning bolt. Believe it or not, nature has cooked up even more extreme versions. Some are way more powerful, and some are just plain bizarre. Just take a look at this. On one side, you have your average bolt. On the other, you have superbolts. These things are super rare, less than 1% of all strikes, but they can have peak currents over 500,000 amps and release more than 100 times the energy. Some are even 1,000 times stronger than a typical bolt. And for some reason, they seem to love happening over the ocean during the winter. And then there's something else. Something even stranger. A phenomenon that scientists have nicknamed dark lightning, and it creates some of the highest energy light that's naturally found anywhere on Earth. Okay, so what is it? Technically, these events are called terrestrial gamma ray flashes, or TGFs for short. Think of them as sub-millisecond bursts of the most energetic light our planet can produce. And in that tiny fraction of a second, they create a beam of electrons and their antimatter twins, positrons, that get shot out of the top of the storm cloud straight into space. We know this because NASA's Fermi telescope has actually seen them. So yeah, I wasn't kidding at the beginning. Lightning really does create antimatter. All right, so after diving into all this mind-bending physics, let's bring it back down to Earth for a minute. What does all this incredible power actually do? And the big question everyone asks, why can't we just bottle it up and use it? Well, here's the first problem. For all the bright light and the loud thunder, the vast majority of a lightning bolt's energy, we're talking close to 80%, is just instantly lost. It's converted directly into heat that just dissipates into the air. But the real killer, the main engineering challenge, isn't the total amount of energy. It's the speed. A lightning bolt delivers its entire payload in about 50 microseconds. To put that in perspective, that's like trying to fill a swimming pool from a fire hose that's only on for the blink of an eye. There is no battery or capacitor we've ever built that can capture that much energy that fast. It would just vaporize. But here's the thing, even if we can't capture it, that energy is far from wasted. Lightning plays an absolutely vital role for our planet. That intense heat, it breaks apart nitrogen molecules in the air, creating something like 10,000 tons of natural nitrate fertilizer every single day. It also creates ozone, which helps cleanse the atmosphere. And on a bigger scale, it's the engine that drives and maintains the entire planet's global electrical circuit. It's not just a flash in the sky, it's a fundamental force of life. And all of this leaves us with a final, really critical question to think about. We know for a fact that lightning is deeply connected to the temperature and structure of our atmosphere. So as our climate keeps changing that very structure, how is this ancient, powerful, and absolutely vital force of nature going to respond? How will it evolve right along with our planet?